Hey guys, so today I'm going to be going over exam prep 11, problem 4. It's going to be on the word search problem. Okay, let's get into this. So the problem just basically goes as follows. Given an n by n word search, so let me highlight some key things along the way. Given an n by n word search, shrink this a little bit, and n words, devise an algorithm to solve the word search in O of n cubed time. Let's make this red. For simplicity, assume no word is contained within another word. So this is important. So we have no nested words basically, right? If we have bear, then the word be, so be would also not be in the try. If you're unfamiliar with word, whatever, right? This section is basically about if you're not familiar with word searches. Basically, the way it works is we have a big grid of letters, right? And some words that we need to find. And your job is basically just to find all of these words inside of this grid. And they can be backwards, they can be upside down, whatever. Okay, so our task is basically to figure out an algorithm that can solve a word search in up to O of n cubed time, right? Okay, cool. So the hint is to add the words to a try, right? So you add the words to a try, and then the longest prefix of operation might be helpful. Longest prefix of takes in a string key and returns the longest prefix of that key that exists within the try. So let's say that our try has the word index, and then we say, I'm just going to abbreviate this as LPS of indexes. So longest prefix of indexes is going to return index. My bad. Index, right? Because basically the longest prefix of indexes that's in the try is the word index. Okay. And if index wasn't in here, if there's nothing in the try at all, then we would just get a null value. Okay. So with that being said, let's actually get into this problem. So we see immediately, the first thing I always notice whenever I do these algorithm type questions is any clues in the instructions themselves that might help us figure out, what how we might devise our algorithm, right? So the biggest clue here for me is this n cubed runtime. When I see, oh shoot, here we go. When I see an n cubed runtime, or when I see any runtime really, I immediately know, okay, this is not only an upper bound for like how much time I can take to solve this problem, right? But also it tells you a little bit about how you might go about solving the problem. Like for instance, for us, right, we can take up to n cubed time, right? And we know that we have an n by n word search, right? So our grid down here has n squared letters, right? So we have n squared letters. So what that tells me is that if I were to just do this totally brute force, right? Just go through each and every letter one by one and do something with it, right? That's a pretty basic, I think, route to go down at first, right? You say, okay, I have n squared letters. Maybe I can just visit each letter and do some work there. And so this n cubed runtime tells us that for each of these n squared letters, we can do up to n work, right? Because that's going to be times n work per letter. That's going to equal our O of n cubed that we were looking for, right? So basically what our runtime tells us is that, we have an upper constraint that we can do up to n work per n squared letter, and we can still maintain our desired runtime, right? Okay, cool. The second thing is, when I tackle algorithm-based questions, is rather than thinking about it in terms of code and CS and Java and how you might actually write, the for loops and the if statements and whatever, one good way to just like start approaching an algorithm question is just thinking about how you would do it if you were actually just solving a word search, right? Or actually just doing the problem by hand. What I mean is, what's like a common strategy that you might use just to solve a word search on your own, right? Without thinking about what a computer is going to do. One thing that I think everyone probably does is, we visit each letter, right? So step one is to visit each letter, right? So we'll start maybe in this top right or top left corner, right? And what we do here is we check each and every direction from this letter, right? So we're going to check down and see if there's any words we can find. We don't see any there. We'll check diagonal. And here we see, oh, okay, I found crystal, right? I check this direction, I found crystal. So now what I do is I cross out crystal from my list of words that I'm looking for, right? And then I move on. I can move this for a second and then check this direction, right? And then, now that I've exhausted all possibilities for this letter, which means I can move on to this letter and check this direction, check this direction, check this direction, so on and so forth, right? And so we go through each and every letter, checking up to 8 directions, right? Because, for instance, this letter has 8 directions, right? But so the general algorithm that you might follow, just, on your own, is you say, okay, visit each letter, check each direction. If word, I'm just going to say, so if there's a word, remove from list and repeat, right? So you can see immediately that even though this isn't necessarily like, in code yet or anything like that, this is sort of a pseudocode version of what we might want to follow, right? Visiting each letter, checking each direction. If there's a word, remove it, and then move on. And so this is actually exactly what we're going to implement in our actual algorithm down here, right? Because as you can see, this visit each letter, check each direction thing pretty closely follows this n cubed runtime that we were talking about over here, right? We're visiting each letter, which means we're doing n squared checks, and n work per letter, which we'll get into in a second. Okay, so now let's actually implement this algorithm. So step 1 is going to be add words to try, right? Just like how the hint says, our first step is going to be to get all of our target words into this try. Okay. Step 2 is basically going to follow this set of steps we created up here, right? So first, what we're going to do is going to say, I'll just use a little for loop here. For each letter in grid, okay? This is going to be kind of like, I'm not going to write out Java syntax. You don't really need that for this one. We just want you to sort of describe the problem itself and how you might, write an algorithm for it. Once you have pseudocode, it's pretty easy to convert that into Java language. Okay, so for each letter, for each letter in grid, the first step will be to, let's just start with a north direction. So check north direction. And what is a check? The check really just means get the string of letters in the north. So what I mean by that is that let's say we're on this letter, right? Arbitrary letter, or maybe even, let's say we're down here, right? Checking the north direction means getting this entire string of northern letters, right? Okay, so we get that string. Let's just call that string S. Okay. Now what we do with B is what we need to do is now that we have this S, the second, so we've checked the first direction, right? We've done this step 2, sort of. We've done part of step 2. Now what we need to do is we need to say, okay, in that direction, we need to figure out if there's a word in that direction. How do we do that? Well, we were given this longest prefix of operation, and that's where this actually comes really in handy, right? So what we can do is we can say, I'm going to take this string S, which represents all the letters from my start point in the north direction, and I'm just going to pass that into longest prefix up. So I'm going to say if LPS of S equals, so basically, let's do this, not equal to null. Let me write this out. And then I'll explain what I mean. Okay. Let me make this a little bit neater. There we go. Okay. So what do I mean by this? If LPS of S is not equal to null. So we know that it's null if no prefix exists, right? So if a prefix exists, then LPS won't be null, and it will actually return the word that we're looking for, right? So for instance, in this example, where is it? Let's say we did here. Let's say we started at this S, and we checked in the, what is this, west? Yeah, the western direction, right? And so we passed the string sohum C into our LPS function, right? What LPS is going to return, so LPS of sohum C is going to return sohum, right? Because we know that sohum is in our try. And so the longest prefix of sohum C that's in the try is sohum. And so that means that we know that we found a word here, right? In this direction from this starting letter, if LPS returns an actual word and not null, we know that that word is in the try. And so we found a word in our word search, right? So actually this remove S from try, this should actually be remove LPS of S. Remove LPS of S from try, right? And then the next step is just to repeat for all 7 other directions. And we're not going to be too specific about like base cases. Obviously, you know, if we're in a corner, there's only 3 directions. So whatever, right? Basically, we can account for special cases later on, but the general gist of the algorithm is this. And then finally, basically repeat until try is empty, right? So when the try is empty, since we initially loaded up our try with all of the words in our word search, we'll know that we found all of the words when the try is empty, right? Because every time that we find a word, we remove that word from the try. And yeah, that's the whole algorithm. So basically, we're basically just implementing exactly what you might think you would do if you were just solving a word search on your own, right? We're basically just implementing the very brute force solution to a word search. So generally speaking, whenever I think a key takeaway from this problem is that if you are solving an algorithm problem of any kind, it's always a good idea to just, before you worry about anything regarding code or syntax or whatever, just sit down and think about how would you solve this on your own by hand if you're drawing down on paper or whatever, right? Just think about the steps you take, and then more often than not, those will help you to solve the algorithm when you're actually doing a CS version. Because at the end of the day, code is written by you, right? And so a lot of the thought processes that you see in algorithms are pretty natural thought processes that you'll just come up with on your own. And yeah, I think that's about it. Thanks everyone for watching, and I'll see you next time.